Los Angeles. Oh, I thought we did that already.
Oh,
Did I not see that a second ago?
You did.
yeah. Well, you saw a different message, but it might be the same.
Okay. All right. So we're being
One
recorded.
is going live, and then one is
Got it. Okay.
recording.
All right. So everyone, remember we are being recorded, so let's not have too much fun. Well, first, most of you, I didn't see anybody really come in since I've been chatting, so you caught a lot of what's going on, so we can go quickly through the Garvey report and all that. Do we have any new people here? This is the first thing I'd like to do is welcome anybody who came to the meeting first time. Nick, how are you doing? Tell us a little bit about yourself. Edward too? Okay, cool.
Hi, my name is Nick Sitchan. My wife and I moved to Santa Monica recently. I was in New York City for 17 years. I haven't been in California resident since 1999. I've been into astro for about 2.5 years, but I'm still definitely, I described myself in the application as a pig on roller skates, but I love it. I've got the bite. I've been bitten by the bug. I'm setting up my rig, and this is my 3rd iteration of my rig, and I'm preparing to photograph Andromeda, and I'm just reading all the forums, and we're thrilled to be part of you guys.
You sound exactly like the club members. Welcome in. I got bitten by the bug. Well, Garvey is a good place for you to come and look at other scopes and bring one when when you're comfortable about setting it up or you need more info. That's where we hang every week.
I will be there.
Okay, cool. Edward.
Yeah. Hi, it's nice to meet everybody. I was a member many moons ago, many years ago when I first moved out here, and then just work and life kind of intervened. And now I'd like to very much get back into it. I've got a telescope that I've been using for quite a while on my own, and it's always more fun to do it with other people. So happy to be back and be observing along with the rest of you. I'm mostly a visual person, but I love listening to, I love learning about photography and watching people do it. It's fascinating to me. And so I like all aspects of it.
Great. Are you available for outreach? Would you be interested in being on that mailing list to go take your scope and do schools and stuff?
Yeah, potentially. I'm mostly working from home now, so I have a little more flexibility, and if that can work with my schedule, sure. Okay. Well, what happens is, when we get I'm sorry?
You're my man.
Hey, Edward, what scope do you have? And if it's not too personal, what decade did you first, what decade in the past did you join the LAAS?
Dave, I'm sorry to cut you off, but I don't want to get into conversations at the beginning here.
I'm happy to answer your questions later, though.
Yeah, let's do that at the end. We always have time. We're going to go through this rather quickly today and not hold up our speaker. I'm sure there's going to be a lot of questions. Got fantastic subject. So we'll get to that as quickly as possible. Is any other new members other than Nick and Edward here? No?
Yeah. My name is Robert. I'm a new member as well.
Hey, Robert, how are you doing? Tell us just a little bit about yourself.
Good. So in a former life, I used to be a deck officer on merchant ships, and I used to use a sextant and take star sights. And I've always been interested in astronomy. So I live here in LA. I think there's a lot of great opportunities here, and I just wanted to see what it's all about and see what I can learn.
Great. Well, welcome in. There's lots of stuff to learn. If you're local enough, again, Garvey's a good place to go hang and meet members that do all the same stuff that you're doing.
Sounds good. Thank you.
Sure.
I think we also have Nick and Xenia.
I'm sorry?
As new members, we also have Nick and Xenia.
Yeah, that was me. Xenia is at the beach right now, so she'll be back shortly. So I'm just here.
Yeah, that was Nick. He's in.
Yeah.
All right, cool. Okay. Let's see. I don't have a whole, I talked about all of the stuff that's really coming up quickly. There's nothing happening at Griffith. They're still not having public star parties. They're trying out a few things, seeing how it works, but there's nothing being announced. They're still open, I think, was it 4 days, Dave? 4 days?
Yeah,
or 5? 4 days
Thursday
now?
to Sunday. Thursday and
Okay.
Sunday.
I'm sorry, I didn't designate which Dave. Actually, I was looking at Dave Yackerson, but thank you, Dave.
I actually work there, so.
Well, so does he.
I've been working there
I
longer.
don't work there. I don't work. I'm with a foundation, okay, and I'm a volunteer, so I know what's going on.
Yeah, that's okay. That's good.
As well as David.
So they're not
David
fully
works there.
staffed. They're not open all the time yet. So they're still doing, no big star parties that
They're working. They're working on it. If we hear anything, we'll let the general population know.
Well, we have, a kind of a regular conversation with Mark Pine over there, and he lets us know, if they're thinking of it's going to happen or not. So far, it's still not. Let's see if there's anything else. So there's not that much happening there. Mount Wilson is a rocking place. There's a lot of things happening there. It's very busy. There's a lot of things to do. All the new members should go to the mountwilson.edu and look at the concerts in the dome and the other things that you can do there. Engineering tours. It's pretty cool stuff. Our 60-inch nights are full for the next one. The following month is the 100-inch night, which is also full and has been for a long time. We haven't had one for, I think, almost 3 years. Last time we had one, I think we were weathered out, so that we didn't get one that year at all. And then we had COVID, and so it's been like 3 or 4 years since we had a 100-inch night. So that's been full for a while, and that's good. And then the next one is the photography contest winners night on the 60-inch. So the next available night is going to be in, I think, October. So October and November are the last 2 60-inch nights that have openings. If you're interested in that, you can go to the website or contact me, Mount Wilson Coordinator, altogether at laas.org. I'll give you information. I don't think there's happening anything at Ford. It's been rained out a couple of times, but I don't think there's anything scheduled right now. Joe, did we come up with something? I talked to Curtis Curtis is here. Talked to him at the meeting.
I'm here.
I talked to you at the meeting.
If we open it up, it'll be in 2 weeks.
Okay, so everyone look
Depending
for
on the weather conditions. Yep.
Okay, so look for an announcement from our communications coordinator on openings that happen there. And she sends out information all the time. Try and stay on top of that. It's good stuff. Let's see. The other thing I wanted to bring up, I see Keith is here. He's in charge of our loaner program, which is coming along really, really well. We're probably maybe a week or 2 away. We've got some contract and payment things to nail down, but we're almost good to go. Keith has been awesome. I think you got like what, 8 or 9 scopes ready to go?
10, and I
10.
finally have a database of it, so I actually can be pretty specific about what it is finally.
Fantastic. And quickly at the board meeting, we talked about maybe having a couple of echelons of loaner scopes, like ones that are like, we wouldn't mind loaning to the public that are not members, other ones that are members only, and ones that are like members only, but boy, you better know what you're doing to take this for a month.
Yeah, that makes
like
sense.
That. So we're going to have maybe a couple of categories on down payment, how much we need to hold it.
That's true. It would be weird kind of like asking for like a $650 collateral for something that's only like a couple $100.
Right. So we're gonna have tiers, and most of those telescopes were donated. So we're trying to get them into the hands of the public. We're not trying to make money. So it's just trying to get them to bring them back so we can get it to the next person.
Yep.
Other than that,
hey, Daryl,
yes.
Just what we mentioned earlier, but this Wednesday night we're teaching the astronomy merit badge. It's our last class of the summer at the Garvey Ranch site, and any members that want to come and set up and be with the club, as we mentioned previously, would also have a chance to help the scouts earn their badge by sharing their scopes on the lawn. And thank you, David. And it's our last one, so thanks a lot. Appreciate it.
Daryl, August 27th.
August 27th, as far as I know, is on. Did you see the email from Norm?
No, I didn't.
Not,
Okay, we're talking about the Star Party,
saw him Sunday.
Party at Mount Wilson, right?
yes.
Okay. Yeah,
Looks like a go.
we got to go on that. They just want to make sure that we have enough people to cover, you know, a couple of people at the front gate, somebody at the gate to the upper parking lot. You know, if we got enough people there, you know, we're good. We're fine with it. Michael Rudy, who's doing the 100-inch that night, chimed in. He said, you know, we're fine. His group's going to be there at 7:30 or 7. Anyway, I picked like 15 or 20 minutes after his time for our group to show up, just to try and separate them at the gate. And we got some good signs for people to hold up for the 3 different events that we're having. So it's going to be, you know, we need to make it very unchaotic at the front gate. So I got some nice big signs that say 100-inch night, 100-inch public night, you know, public Star Party, 60-inch night. So when people drive up, they can see which section they should at least get close to.
I'll be at the front. All
right.
I'll be at the gate with a couple of other people. So we're
All right.
good.
So you know, I'll make sure that there's a list of people for that, and you know, all you guys stay in the loop. You know, I'm getting it started, but I'm not going to be very involved. I'm going to be in the 60-inch dome that night with an LAAS night. So you know, I got my own whole stuff to do.
That. I already know. Yeah,
like that.
You won't be affected. We'll take care of everything for the lower gate stuff, for the upper parking lot. We'll take care of it all.
Perfect. Okay. Tim, you have anything to add about Garvey or Mount Wilson?
Well, you already took care of Mount Wilson. It's mostly our observing nights. We are going to do a Halloween science night on October 29th. Gio's already got people lined up, and I know some of you are going to go off to nightfall. Well, too bad, you're going to miss the real fun, because you know nightfall is dark, and you know who needs that.
And it's 3 nights.
But it's a Halloween science night, and new members get together and everything else you can think of. And I don't know exactly when we're going to start, but sometime in the afternoon probably. And be there late, and you know, come dressed up as your favorite scary thing, and I will come looking like Dumbledore, and it'll be Stump Dumbledore night. Try to ask me a question that I don't know the answer to. That's the 29th, just before Halloween. So there you are.
Everyone got that? Okay, so I will. I want to introduce unless anyone has anything else, I'm going to move on and introduce our guest speaker for the night. And right after that, I'll put the drawing information in the chat so that everyone can go and sign up for our prizes. I think that's it.
Your telescope looks bigger than yours, Daryl.
Zali, do you have the screen up? Are you sharing screen for Spencer's slide? Or maybe I need to do that. Let's see where we are.
You're muted. You're muted.
Whenever you want to start sharing, just start sharing.
Okay.
Yeah, share screen.
Okay, I'm getting there. Just want to be on the right screen before I share it. See, where did that one go?
What?
Well, let's see. I don't have the right thing here, I don't think. All right, there we go.
The 29th is for Garvey, guys. The 29th is Garvey, and the 27th is for Mount Wilson for the start party. And you can arrive there early, like 5 or 6 o'clock or 7 to set up on the upper lot.
Okay. Everyone can see our guest speaker?
Got it. Yep, you're in.
Okay, great. Okay. I'm not going to read all this. I'm going to just give you all a moment to go through this. Tim, I think has, this was one that we had to schedule a couple of times because of something or other?
Well, yeah, this is one I had a hard time finding somebody who would get a speaker, but we've heard talks about the 30-meter telescope, but they're not doing anything. These people are building it and they're getting ready and they're going to actually start looking at stuff. So we should actually pay more attention to them, you know. So there you are.
Well, fantastic. Dr. Sitarski, would you like to take over and start your talk? And I'm sure there's going to be a lot of questions, so we're going to have a lot of time for that. And can't wait to hear what you have to say.
Yeah, sure. Let's see.
You'll have to.
Oh, wait a minute. I have to stop. I have to stop sharing. Hold on.
No, you don't. It doesn't. She's got it. She's good.
Oh, okay.
Can everyone see the proper screen?
Yes.
Yes.
Or are you seeing the presenter mode or the normal mode?
Normal mode.
Awesome. Thank you. So as you read, my name is Breann Sitarski. I'm currently the optical systems scientist and deputy project systems engineer at the Giant Magellan Telescope. And so what that means is I'm in charge of the optical performance of the observatory and making sure that the observatory we promise to our funders and to our partners is what's actually delivered. And so I participate in all the different optical elements. And today I'll be talking of giving an overview of the Giant Magellan Telescope and why it's really, really important and what we hope to do with it. So I want to zoom back a little bit and talk about what's really motivated some of this work. So the last few decades have seen incredible advances in astrophysics from some of the observatories that have been developed. One of the first ones was Hubble as one of the pioneers of this astrophysics revolution, but also one of the pioneers of this, of really exciting the general public with these awe-inspiring images that you can obviously see here. The Hubble Space Telescope is really remarkable. It's a 2.4 meter or about 8 feet telescope, and it orbits around the Earth. It started taking data in 1990, and it is quite literally still in use. I actually got some of the data from my thesis project when I was studying at UCLA from Hubble, and the data is quite remarkable. It's allowed us to see nests of star formation, which you can see here, clusters, we can see colliding galaxies, and we have been able to, with unprecedented clarity, see some of the objects within our solar system. Recently, we deployed another space telescope, the James Webb Space Telescope. This is slightly larger aperture. This is a 6.5 meter telescope, and this is a successor to Hubble. It's since produced incredible images in the infrared. And so what the infrared does is it cuts through a lot of the gas and dust that you might see. So on the left in this image, you can see this is the view from Hubble, and on the right is the view from JWST. One of the few things to take away is that the infrared allows us to see through this veil of dust in the Carina Nebula, which is why compared to the left to the right, you can see many, many more stars. But it also, with its larger size, it's a lot more sensitive. So we're able to see more stars that way. But we also get this incredible resolution where you can start seeing really the tapestry of the Carina Nebula. It's also allowed us to go and see evidence for water in the atmosphere of WASP 96b, and it's just going to continue to revolutionize the kind of astrophysics that we're doing and what we're going to be able to discover as time goes on. To compare HST and JWST, these are the two apertures. So HST, like I said, is a 2.4 meter diameter. So from across the diameter, it's 2.4 meters. JWST from one side to the other is about 6.5 meters. And there's a human for scale. But these are in very, very different orbits. So Hubble is in an orbit about 340 miles off of the Earth, whereas the James Webb Space Telescope is much further away. And the reason for that is because JWST needed to get away, because it's a space telescope, it wanted to get away from all the heat signatures that could come from the sun, the earth, and the moon, because all of those are giant heat sources. And the objective of Webb is to see the heat signatures of the universe. So we've had these two revolutionary telescopes. The most recent one is extremely revolutionary in what it's going to do and in what it's already done. But of course, not all telescopes can go to space. That would be great if it could, but obviously it can't. So we have a lot of ground-based telescopes, and I'm sure many of you know about these. We have the Gemini telescope. There are two of them, an 8-meter in Hawaii and an 8-meter in Chile. So Gemini North and South. We have Palomar Observatory, which if you have not visited, I highly recommend it. It's a beautiful observatory, and that's a 5-meter down in San Diego County. We have the Twin Magellan telescopes. These are 6.5 meters telescopes in Chile. 4 8-meter telescopes that are part of the Very Large Telescope Array, and these are also in Chile, but in a different part of Chile. The Large Binocular Telescopes, also 8-meter telescopes. These are on Mount Graham in Arizona. I often get told that this picture in particular makes it look like WALL-E. And on the summit of Mauna Kea, we have a slew of telescopes, including one of the Gemini telescopes, the Subaru telescope, and the twin Keck 10-meter telescopes. So we have all these very, very large telescopes. And the point of being on the ground versus being in space is that you can build these telescopes to be larger because you don't have to launch them from Earth. So to put things in perspective, one of the mirror segments of the Large Binocular Telescope and the Giant Magellan Telescope that I'll describe later, one of those segments weighs about 38,600 pounds. JWST's launch weight was 13,600, and Hubble's, which didn't have to travel as far away, was about 24,500 pounds. So one single segment of the Large Binocular Telescope or the Giant Magellan Telescope is at least 1.5 times the launch weight of Hubble. There are pros and cons to having an observatory on the ground, though. The pros, like I said, you can have these larger, heavier mirrors. You don't have constraints on shipping things to space. The larger mirrors, like we saw with JWST, means higher resolution. You can see these finer details, and you can also get more sensitive measurements. And most importantly, you're able to service things on a long-term basis. You can rotate the instruments in and out. You can go and do fixes and everything to make it have a long lifetime. The cons are that the atmosphere blurs the image, and that's what produces twinkling stars. So in this video that I'll show you on the bottom right now, this is a still frame of a star that was taken very, very quickly. And this is peering through at a star through the atmosphere. When I turn the video on, you'll see that it's going to very, very rapidly blur. And this is actually what's happening. And this is why we perceive stars as twinkling. So you can see that it's moving sporadically around, and that's just because that's how the atmosphere is messing with the light rays as they approach us from space. So this is one of the biggest cons, is that while we love the atmosphere for our ability to breathe, it's kind of problematic when you're trying to do high angular resolution imaging of space. But we have a fix for that. So we have something that is called adaptive optics. And this movie is going to show adaptive optics, particularly the system at Gemini, but it's very similar to other systems. So we have the light propagating down the telescope to the adaptive optics system. And for Gemini, that sits at the back of the telescope. It's going to come down, and we're going to see the inside of the adaptive optics system here. So we attach a computer so that we can see what the image is going to do. And the light comes down, gets folded, and hits a few mirrors and comes to the computer so that we can visualize what the data is doing. And you'll notice that it's sporadically moving around just like it was a few minutes ago. And we've split the light We have red light here and blue light coming down. Our science light in this case is this red light we're observing in the infrared. You can see the light coming in and how it's very distorted, but we can send some of the information that we're using, the visible light, we can send that to this special mirror that adapts and uses that information to make those deformed wavefronts actually flat. So instead of having Lay's potato chips, we actually get these flat potato slices. And once we turn adaptive optics on, we get this very steady, very tight image that is consistent with the diffraction limit of the telescope. So to put it in another way, I did my thesis work on the Galactic Center. I spent a lot of time looking at the Galactic Center. And this is some of the work that received the Nobel Prize in Physics in 2020. If you look at this very center of the Galactic Center where the black hole is, it's about right here where my cursor is. You can see that this kind of just looks like a few giant blobs that are in the region. And that's true when we have the atmosphere disturbing those images. But when we turn adaptive optics on, those giant blobs end up going to individual stars. And you can see that there are many stars in this field. So the contrast, the comparison really is without adaptive optics, your information is very, very blurred. But once we turn that on, we can start seeing all the different components of what makes up these blob-like features. Another way of looking at it is this is how we would see Neptune without adaptive optics. Once we turn the adaptive optics on, system on at Keck, we actually get this beautiful image of Neptune. So we're able to see very, very fine features. And this really takes advantage of the size of the telescope. We have lots and lots of telescopes that have gone up, from space telescopes like the James Webb and Hubble and Kepler, for instance, to many, many others that are on the ground. And you can see a whole array of them here. However, new technologies and scientific needs have really pressed for larger and larger ground-based observatories in order to address the scientific needs of the community and the scientific interests. So we have 3 extremely large telescopes that are the next generation of telescopes that that are coming online within the next decade or 2. The reason we want these larger telescopes, just to bring home the point, is that a larger telescope will give you finer resolution if you're able to correct for the atmosphere. That's what that caveat asterisk is. But you also get higher sensitivity. The analogy I like to give is that a telescope is kind of like a rain bucket. When you have a very small rain bucket, even if you put it out in a monsoon, you're only going to collect a certain amount of water. If you put it out in the same monsoon, you're going to collect a whole lot of water if you put out like a kiddie pool or something instead of a like Home Depot bucket. So when I say extremely large, I quite literally mean extremely large. These are the mirror, a depiction of the mirrors from the Giant Magellan Telescope, which I'll call GMT now for short. And here on the left is a human for scale. I've been to the mirror lab where we construct our mirrors, and I can tell you that it is actually ridiculously large, and it's quite intimidating seeing 3 of the segments put together. If we turn the side face view face forward, this is what the pupil of the Giant Magellan Telescope looks like. And to put the sizes that we were talking about with Hubble and JWST into perspective, the center circle where our light comes down after hitting the secondary mirror, this hole is the size of the Hubble Space Telescope. And JWST's entire mirror array would fit into one of our segments. And you can fit a few people across each one of our segments. In total, our diameter is about 25.4 meters across, and it has a huge collecting area of about 368 square meters. So like I said, GMT will be one of 3 extremely large telescopes. We will have the European Extremely Large Telescope located in Chile. This will have a diameter of about 39 meters. Sorry about that. The 30-meter telescope, which I heard you heard a little bit about before. This is will be in Hawaii or the Canary Islands, and this will have a diameter of about 30 meters. And then, of course, the Giant Magellan Telescope, and this will be in Chile with a diameter of 25.4 meters. And this is the one that I'll keep talking about. So the GMT has a lot of different institutions from all over the world that actually participate in this project. So we have many from the United States in Arizona, Texas, Chicago, Harvard, Carnegie, so on and so forth. And we have partners in Brazil, in South Korea, Australia, and Israel. And the site will be in the Las Campanas Observatory in Chile, which you can see right here. This is part of the Atacama Desert. And to compare what GMT will do compared to Hubble and JWST, this is a series of simulations that we've done. So one of the reasons we want to build GMT is that this, like I said, this is an extremely large, very large diameter telescope. So the resolution, so those very fine details we'll be able to see, will be about 10 times better than Hubble and about 4 times better than JWST at their specific wavelength. And the sensitivity will be about 14 to 200 times better than the current class of telescopes like the Gemini, the Keck, the Large Binocular Telescope than I was showing before. I want to focus on these images on the bottom. On the left, this is what we get when we don't correct for the atmosphere. So you can see that it's just a bunch of blobby-like figures. When we go to space where there's no atmosphere to contend with, you get what a 2.4 meter telescope looks like of the same cluster. This is what we anticipate JWST will see. Again, 6.5 meters versus 2.4, much, much finer resolution. But when we go to the GMT and we have adaptive optics, this is the sort of resolution of the same cluster that we anticipate. So we'll be able to see finer details with higher sensitivity. This is another comparison. So this is on the left, this is a redshift galaxy with a redshift of about 2 from a high resolution simulation. And you can see the very, very fine details throughout this simulation, particularly in the core of the galaxy. This is what data currently looks like from the Gemini telescope. That's the telescope that we had that adaptive optics movie from. Once we turn GMT on with our adaptive optics, this is the sort of data that we anticipate we will get. So we do start resolving some of those fine features of the core of this galaxy with the GMT. So I hope I've shown so far that this will really, really be a revolutionary instrument. But if we want it to be a revolutionary instrument, we have to put it in a great location. Location really, really matters when it comes to putting these very large telescopes. We need a site that is dry. We can't use if the telescope if the humidity is too high. We want it high so that we can get above most of the water vapor in the atmosphere. We also need the fundamentals like electricity, internet, water, gas, and so on that we can put up there. And of course, astronomers are going to want to fly in and take data. We're going to have a staff there that will also need to rotate sometimes. So it's also ideal if it's close to an airport. So our site is in Las Campanas. It's not so far away from Santiago. You can fly to Santiago in Chile, take a small flight to La Serena, and then it's a few-hour bus ride. This is what the site looks like. So this is a movie that shows how the site progresses through time. And you can see that we've leveled the site several years ago, actually. And a few years ago, we started doing hard rock excavation. So this is where our pier will be, right over here. Let me pause it. So this is where our enclosure will be. This hole in the center is where our pier will be. This is our residence hall where our astronomers will stay and where about 100 staff live pre-COVID times. This is where some of our support buildings will be. And this tower right here actually is currently taking data. And I actually analyze the data once a month. And so that allows us to see how the weather patterns and everything are changing on the site. And we can monitor to see when storms are coming in and so on and so forth. So we've made a lot of progress on the site. This is a pretty current movie. You can see that we've done quite a lot of digging. This is a turbulence profiler. So we're also seeing, taking data on the atmosphere above the site as well, because that is something that we really care strongly about. This is what the site looks like after excavation. Like I said, here's where the enclosure will be. This is where the pier is. You'll notice that we have a bunch of space over here. And the reason is that if we want to build another 25-meter telescope, we have plenty of space to do it on the site. So we could put another GMT and kind of do an interferometer kind of thing, just like the Keck telescope, the twin Keck telescopes do, or something in that manner. This is what we anticipate GMT will look like upon completion. So that giant circle you saw, this is where our enclosure will lie. Here are summit support buildings. Here's another one. And here's where some of our utilities are, like our water and such. So getting back to the primary mirrors, which you can see right here in its configuration, each mirror segment is about 8.4 meters across and or about 27.5 feet. And like I said, the entire aperture is about 25.4 meters in diameter. And one of the cool things about our telescope is that each one of the mirror segments is fabricated at the University of Arizona, which I'll show in just a second. But I always like to put this picture up too, because this really puts, for me, you know, going to the zoo growing up, this really puts it into scale. Giraffes are extremely tall, and one of our mirror segments still is larger than a giraffe. So in order to actually make sure that the telescope stays put together, we can only really move the mirrors and bend them as about 100 nanometers, which is extremely, extremely small amounts. So we have to make each one of our segments extraordinarily stiff. So one of the ways we do that is making this honeycomb shape. And so this is just like a ceramic-like material. And this is setting up the mold for making one of our mirror segments. So this honeycomb not only makes it stiff, but it also lightweights it. Each mirror segment is lightweighted about 80% of the weight if we did not have, or 80% of the weight is reduced if we didn't have this honeycomb structure. But each mirror segment still weighs about 17 tons or about 38,000 pounds. Each one also takes about 4 years to make. So I'm going to show this video, which shows all of our mirror segments are created underneath the football stadium at the University of Arizona. This is us creating one of the molds for one of our segments. So there we go. We put in the honeycomb structure, and then we start lying by hand the individual pieces of glass. So this glass is a super pure form of borosilicate, which is what Pyrex used to be made out of. It's still made out of borosilicate in Europe, but not in the US anymore. And what this, the reason we need it ultra pure is because any of those impurities could cause stress to the glass. And so this is very lovingly hand laid glass. And then we put it in the spin caster. And the reason it heats up and we spin it. And the reason we spin it is so that it gets the parabolic shape that is necessary in order to make the optical design work. So the glass melts and it goes in between the honeycomb structure. You can see the glass coming up and then going down. And once it's all put together, we take it out of the oven and we do a very, very fine polishing of it. The fine polishing takes a long, long time. It's very similar to sandblasting it. And the reason we need it and the reason it takes so long is because we can't have more than about 20 nanometers RMS error over the entire surface of the mirror cell or of the mirror segment. Then we pack it all up, and we are currently storing 2 of our mirror segments in the Tucson hangar. So one of the coolest parts of my job is that I'm involved in approving the optics and making sure they meet the very stringent requirements. And so I get to visit the mirror lab quite often. So this is one of the stages of polishing. You can see that there's this like sandblasted material as they very, very finely polish it down. So we have these giant segments that are quite heavy, despite being 80% lightweighted. And so we have a very complex support system to hold them to. We need to be able to rapidly adjust their position to fix alignment. And so we have these things called hard points, and these work together to bulk move the entire mirror in translation, and then also in some tips, tilts, and slight rotations. We also need to be able to rest the mirror when it's not in use. So when it's not in use, it actually drops down and rests on these things called static supports. And these have to be stiff enough to hold up the 17-ton mirror segment. We have these triple and single actuators that go and actually bend the mirrors themselves. And they are meant to adjust for any small aberrations that we might see. And by small aberrations, I mean low order. So like focus errors, for instance. Instead of applying a strong force to one single point on the mirror, we have these things called load spreaders, which literally just spread that force load out. On top of that, we have to keep these segments thermally controlled. So we have all of these nozzles that point into all the holes. You can see that in this cross hatching here. And it acts as like an air conditioner or a heater to make sure that the mirror segment itself is very, very close to the temperature inside the dome. And that's because if it's not, it can cause a lot of optical aberrations, but it can also put a lot of stress on the glass if it's too far away from the outside temperature. Like I said, the support actuators will be able to bend the telescope, and they correct for small, slow varying errors every 30 seconds. And we sense these using something called the acquisition, guiding, and wavefront sensing system. So this is a really, really complex, but really interesting system. And what it does, this is the view that it will see, is it collects light from guide stars, these bright stars that tells the control system how to adjust all of our mirrors, how to move them, and how to bend them. So we do that using something called a wavefront sensor. So a wavefront sensor consists of a lenslet. So it's literally a bunch of small little lenses that take the light and focus it down. So on GMT, it will look something like this. You can see a whole bunch of dots, and this is a result of focusing the light through these small lenslets. And once we have that, we're able to correct for aberrations. So if one of the mirrors is tilting, for instance, the spots might move back and forth subtly like this. The goal is to get all 14 segments, because we have 7 primaries and 7 secondaries, perfectly aligned with the correct figure. If we put astigmatism or a potato chip-like figure on it, you can see that those dots get stretched out. So we're able to figure out, based on what the dots are doing, how to correct each of the individual mirror segments. So we'll make some of these corrections with our adaptive secondary mirror. So we have a primary mirror, and each of the primary mirror segments have a counterpart in the secondary mirror. So we have 7 secondary segments as well. And the cool thing about our secondary is that it's fully adaptive. So when I was showing that adaptive optics animation and the mirror was literally bending in response to the atmosphere, every single one of our secondary mirrors will do that. Each of these mirror segments are about 1 meter across, and they have 675 actuators that push and pull on the mirrored surface. They move about 1,000 times per second, and they're meant to correct atmospheric turbulence. If we take one of these segments and blow it up, it looks something like this. We have a positioner to bulk move it. We have a cold plate so that it maintains the right temperature. We have all of our actuators, and these are voice coil actuators, so they're actually magnets. A reference body so that it can move with respect to something, and a face sheet. And this is a 2 millimeter thick piece of glass that is aluminized on one side of it. Like I said, this is about 1 meter in diameter. So we have our primaries, we have our secondaries, we need something to support it. And so we have this giant mount. And the mount is really the heart of the telescope. It holds everything. It holds our mirrors, it holds our instruments, it holds all the utilities, it holds our metrology systems, and so on. And the mount is huge. It's about 22 stories high, and you can see it in comparison to the shuttle at the California Science Center. It's quite massive. Our partners at Ingersoll Machine Tools in Rockford, Illinois, are currently constructing it, and they literally had to construct a new building in order to start fabricating our mounts. So when I say extremely large, I mean so large that we don't have the facilities available right now in order to construct it. So like I said, we have 7 primary mirrors and 7 secondary mirrors. The telescope is going to move. I mean, we've all seen telescopes move as we track objects in the night sky, but we have to make sure that those 7 primaries and those 7 secondaries stay perfectly aligned. If they don't stay aligned while we're observing, then we're not going to get those high quality images that I showed beforehand. So the solution that we came up with is a bunch of 3D laser metrology systems that have laser trackers and 2 types of different interferometers to give us high absolute accuracy and high relative accuracy. So the first one is our laser tracker network. And this will literally be 4 laser trackers. 3 of them are bolted onto our truss that supports our secondary. And they will have lines of sight. We'll only use this during engineering time, so never when we are actually taking science data. But they will coarsely align all the segments to a reference axis that we have. We'll be able to use these to help us figure out where everything is with respect to each other. And our basis is this, along the base of the enclosure, we have these very, very stable standoff points where we'll be able to figure out and encode a coordinate system on here. So whenever the telescope moves, especially if there's a seismic event or something, and those are plentiful in Chile, whenever the telescope moves, we'll be able to see where it is by having the laser trackers look at this coordinate system that's encoded on these spikes that you see. Then we have a series of interferometers that measure between the mirror segments. So we have these are infrared lasers. We use these at the start of observations, but never when we are exposing any of our science instruments. And these measure the distances, and we're able to figure out where all of the segments are with respect to each other. You can't really see it in this view, but we also have lines in between as well that are part of this setup. And this is a better way of looking at it, where we have laser lines that go in between. You can see some of these pink areas over here. Those are all the pairs. We have 48 of these pairs, and they all measure the segments relative to each other, because in order to reach the diffraction limit to get those very beautiful images that I showed earlier and I was bragging about, we have to make sure that the primary mirror segments stay phased. So they can only be moved with respect to each other by a very small amount. In terms of phasing and aligning the telescope, we're going to check all of that in a method similar to what JWST does. So some of us may have seen this image. from JWST where they're going through their alignment process. And we're going to do something similar. So this is called phase diversity, where you take each of the mirror, you have the initial position of each of the mirrors, you put it out of focus, you bring it back into focus, and then you put it out of focus again. You can compare the segments and then figure out, or you can compare those 3 images and you can figure out how far to move the telescopes or the individual segments so that they're all in phase with each other. So we're going to do something very similar. So once we have all the pieces put together, then we need a large place to put the telescope. And for that, we have an incredible enclosure that has been designed. So this is what we anticipate that the enclosure will look like once we do complete the telescope. Hopefully it won't be open during the day though, hopefully. And when it's done, some of the really key features of it is that it has these vents that will be able to open and close, that allows wind to go through. And it also has a wind screen that comes up in case we get high winds. I want to pause hold on. I want to pause right here. So this is actually what the site will look like. So we'll have a series of buildings that go as you take the access road up. You'll have some quarters down here. You'll have some offices down here. And of course, you'll have the telescope and the main support building. This is where the optics will get recoded, for instance, and where we'll store things. This is where a bunch of labs will be. And our utilities will be over here. Oops, sorry. To put it in perspective of how big it is, because go Bruins, this is what the enclosure looks like in comparison to the size of a football field and specifically the Rose Bowl in Pasadena. It's quite huge. So I think I said it before, the height of this is about 22 stories. It's quite high. And one of the reasons why it's quite high is because every few years, we have to take out each of the mirror segments one at a time. We'll do it in phases to recode it. So to re-put the aluminized layer on there. And we're going to have to do that about every 2 or so years is what we're baselining. So there's this, in this bar you see right here, there's a giant crane that reaches overhead, dips down like one of those giant hand things from Toy Story, pulls up the mirror and then moves it away. This is what the this is what our new contractors anticipating the enclosure will look like. You can see that there's all this lattice and support structure to really make sure that this is a very robust enclosure. This is what it will look like closed when we open it. And like I said, we'll have a wind screen in case there are very, very high winds, but we still want to take observations. This is meant to minimize any wind vibrations that we might see on the primary mirror segments. There was a lot of thought put into how to actually optimize the design of this enclosure. So we used something called computational fluid dynamics to figure out, depending on the wind orientation and the temperatures and a lot of other factors, what the optimal enclosure design would be. So what this is showing is how the index of refraction of air, or the atmosphere of the air rather, is changing within the dome. And you can see that it's actually quite remarkably different than what's happening outside. And I think that's something that not everyone always appreciates, is that the dome itself is its own environment, and it's not always one-to-one with the outside, especially when you have a dome as large as we do. We also will have a viewing gallery if you guys ever want to come and visit. And this will not be occupied during observations, of course, because we don't want to disturb any of the observations. But this will allow you to see a top-down view of the telescope. So on top of all those things like domes, the atmosphere in the dome and everything, we also have to deal with a lot of seismic events that happen on quite a regular basis near the GMT site. So the site experiences about 6 earthquakes a month. This is not like any crazy earthquakes or anything, but it's something that we have to really take a lot of care into. And so what we use are these seismic isolating bearings that are essentially just like pendulums. In fact, the prototype and the initial use of these pendulums, sorry about that, was at City Hall in Pasadena. So as an earthquake hits, the whole telescope, this whole pier, this whole area, including the telescope mounts, which is attached to this, will just very, very gently move. But because it moves with respect to the ground, that's one of the reasons why we need those metrology systems to figure out exactly where the telescope is if a seismic event does occur. So we have all the different parts of the telescope. We have the main body of the telescope, but if we want to take data, we actually need instruments, because the instruments are how the scientists actually get the data. So many of the instruments that GMT will have are spectrographs, but we will have a few imagers. And a spectrograph basically takes like the light that we observe from stars and breaks it down into the individual wavelengths. And one of the advantages of GMT is that it's very wide field. So this has a 20 arc minute diameter. In comparison, the size of the moon is about 30 arc minutes. And instruments have a set of scientific goals and associated requirements that they've put together with different design trades. And most are pretty complicated given the size of GMT. And you can see that from this view right here. GMT itself has a lot of different science cases. We have literally a whole book on the different science cases that we will have and we will be able to enable with GMT. Those range from exoplanets and planet formation, the birth of stars like we saw in the Carina Nebula, the death of stars, so supernovae, and collisions and such, building the Milky Way and its neighbors. We have galaxies over time, building galaxies from cosmic dust, cosmology in the dark universe, and the very, very first part of light and when the universe was reionized. So, like I said, we have a book, you can find it on our website, called the GMT Science Book, and it steps through all of these science cases and how our instruments go and address those. We have a series of first light instruments, and I'll talk about those briefly. So the first one is GCLEF, which is the GMT Consortium Large Earth Finder. This is being developed at the Harvard-Smithsonian Astrophysical Observatory in Cambridge, Massachusetts. This is a visible light spectrograph, so it is going to act like I discussed. Hopefully some of you recognize this album cover. Where light will hit a prism and then be dispersed into its different wavelengths. This will have an extremely high spectral resolution, and its main scientific goal is to actually enable the founding of planets within habitable zones. This is what the optical layout looks like, and currently they're fabricating. They're actually in fabrication, so they're procuring some long lead procurement items, and they're starting to put the pieces of GCLEF together. You can see two of the science teams and instrument team people down there, and that's the size of one of the lenses that actually goes into GCLEF, so you can really get a sense of the size of it. So GCLEF will revolutionize the study of Earth-like worlds. And so this is a diagram showing the temperature of planets versus the period that they orbit around their star. What you see outlined in red is what we can currently determine, where we can accurately and currently determine masses with our current 8 to 10 meter class telescopes like our Geminis and our Kecs. However, with GCLEF, we're going to open up a lot of that parameter space, and we'll be able to observe a lot more of the higher temperature and also the longer period stars, planets orbiting around the stars. So this will really be quite impressive and really enable the next generation of extrasolar planet science. Next, we have something called GMT NIRS. This is the GMT near infrared spectrograph. This is an infrared spectrograph, and it's actually a really interesting design. So all the optics sit on a single cryostat, which you can see here on the in image B. If we rotate that so that it's facing up, this is what it looks like. And each one of these arms actually covers a different wavelength regime, but they all take data simultaneously between 1 and 5 microns. So this is going to be helpful in following up some of the JWST observations, for instance. And this is under development, and it's being led by UT Austin and the Korean KASI consortium. It's a really, it looks quite simple, but it's actually quite complex in order to get all of these things to line up. It also needs to be cooled down quite a bit because it goes out to this 5 micron regime, which is one of the reasons why JWST had to be sent so far away from the Earth and the sun and the moon. There's only one moving part in the entire instrument, so it's trying to stay as simple as it can be. And it will use adaptive optics to get the very high resolution, high spatial resolution spectra. In order to develop this instrument, the team at UT Austin actually had to develop this new type of prism, sort of. And that's what you can see here. So they had put together some of them in quite a while ago, and they're currently developing the science grade. They're called immersion gratings, made out of silicon right now. And those are currently being tested and should be ready to go. And this instrument is based off an instrument that is currently at one of the Gemini telescopes. And one of its goals is to do something very similar to what I showed with WASP-96b and JWST. It is going to enable the studies of the composition of exoplanet atmospheres. So we'll be able to see a bunch of the water signatures that we talked about, but also oxygen, carbon dioxide, carbon monoxide, a lot of different organic chemicals that will really help revolutionize how we see the atmospheres around these extrasolar planets. So that's quite a compact instrument, but our next instrument is actually quite large. So this is called GMAX. It's the Multi-Object Astronomical and Cosmological Spectrograph. This is a human for size. And this is a visible light spectrograph that has medium spectral resolution, but a very wide field of view. So it will be able to take a bunch of spectra all at once across about a 7 arc-minute field of view. And this is currently being developed at Harvard-Smithsonian as well. One of its main science cases is being able to discover spinning supermassive black holes in the local universe. Supermassive black holes very, very far away, and maybe even look for intermediate mass black holes that we haven't been able to find. It will also allow us to infer the geometry of the emitting material from black holes, and by getting these very, very sensitive, so very, very deep spectra, and being able to fit models to it. We'll also have GMTIFs. This is the GMT integral field spectrograph. This is a near infrared, low resolution integral field spectrograph. And integral field spectrographs are very, very interesting. They take a picture and they cut it into different chunks. And then they're able to disperse these chunks across a prism so that for every single one of these chunks, you get a full spectrum. So these these integral field spectrographs are really workhorses in that you're able to get images like this, but you're also able to get spectra. This is also quite a compact instrument, and this will be enabled by adaptive optics as well, so that you can get really, really fine resolution on your images. This is an interesting instrument too, because it's divided into 3 different chunks. So we have some wavefront sensors in the front, we have an imager on the top, and we have our integral field spectrograph on the bottom. And this will have a very, very small field of view, about 20 by 20 arc seconds, to enable us to do this integral field spectroscopy. And this is being developed by our partners at the Australian National University. And this science case is very near and dear to my heart. It will be able to enable high sensitivity studies of the environment at the Galactic Center. So as I mentioned before, the discovery and the characterization of the environment around Sagittarius A star, the supermassive black hole, was awarded the Nobel Peace Prize, the Nobel Prize in Physics by Andrea Ghez and Reinhard Genzel. And what they used adaptive optics observations at both the Very Large Telescope Array and at Keck. And what GMT will be able to do is provide very high signal to noise ratio images and be able to get the velocities of all of these. So to put it into perspective, this is what we currently get at our 10-meter class telescopes. But when we go to a 30-meter class telescope, this is what we'll be able to do. And we'll be able to map the orbits of these stars as they go around the supermassive black hole. And that will allow us to put further constraints on the black hole and the environment in which it was formed and in which these stars were formed. We also have one of the cool functionalities of our visible light spectrographs is that they can be fed by fibers. And so we have this robotic fiber positioning unit called Manifest, the mini fiber feed. And this was actually prototyped on the UK Schmidt telescope by Macquarie University and the AAO consortium. So this is part of Australia. And what you see here are robotic fibers that move by vibrating, and they move very, very quickly across these glass field plates. And the lights that you see are so that a camera located above the fiber positioner can actually see where the individual star bugs are. That's each of these fiber robots are called star bugs. And so this will enable us to get a bunch of galaxies all at once, or a bunch of stars, whatever you're observing, but you can get many of them all in one shot. And this will feed GMAX and GClef within our first generation of instruments. The prototype on the UK Schmidt telescope went very, very well. And they're currently working out some of the bugs that they had for Manifest to go on GMT. And Manifest will have the full 20 arc minute field of view. So to put it into comparison, this is what JWST's field of view is. This is what one of the Keck fields of view that has a very similar instrument to GClef and GMAX. And this is what the Roman field of view is. It's a very, very large field of view, but we'll be able to do very, very excellent follow-up of some of the Roman data with Manifest and with it interfaced with GClef and GMAX. We have a few other instruments too. We have 2 engineering cameras to ensure that we meet all of our requirements at first light. These are called ComCam for our commissioning camera, and our adaptive optics test camera, or our AOTC. ComCam will be used for the SING limited, and the AOTC will be used for our adaptive optics observations. We have 2 other instruments that are currently under consideration. One is called GMAG AOX, and this is following on a very successful campaign from the University of Arizona on MAG AOX down at the Magellan telescopes in Chile. This is an extreme adaptive optics system for visible light, high contrast imaging. So this will be able to take images of Earth-like planets around cool stars. This is what the optical setup of GMAG AOX looks like. It's quite complex, but one of the cool things is that, that its whole concept is to split each one of the segments of our telescope and put it on a different deformable mirror to adjust for all the turbulence that we see to get at very, very high contrast. The other instrument under consideration is something called SuperFire. This is an efficient single object near infrared spectrograph. So it will be the near infrared complement to GMAX or GCLEF. So I wanted to leave plenty of time for questions. So just to summarize, the GMT will help revolutionize our understanding of the universe. It's a large, doubly segmented telescope, and it truly is an engineering marvel. When we're talking about these kinds of masses, these kinds of sizes, it's incredible. And it's a problem, and it's a huge, very interesting problem, and I learn something new every day at my job. It will truly have unprecedented resolution and sensitivity, and the consortium that's building it and designing it consists of a large collaboration of countries and institutions and they are truly necessary to make GMT a reality. And our first slide is about 2030, and I put an asterisk there because things could change, but that's what we're hoping for. So with that, I'll take any questions.
Breann, thank you very much for that talk. It was outstanding.
Thank you.
You get to play with some really nice toys.
Yes, I do.
It was really good. You got a lot of really good compliments in chat. So everyone is very, very pleased with this. It was excellent and very professional. And I'm going to open it up to questions, which I'm sure there will be plenty. Thank you.
Thanks.
Okay, you guys can unmute and ask questions.
Hi, Breann, can you hear, Dr. Sitarski, can you hear me?
Yeah, you can call me Breann. That's fine.
Breann, great. Question, I hope this doesn't sound dumb, but so is it possible with there's so many telescopes coming in the next, decade that you showed us, would it be possible to somehow coordinate for some use cases, some of these beautiful 30-meter class and, bigger scopes around the globe to sort of simulate the Earth-sized disk like they did to resolve the 15 solar masses for Cygnus X1, for example, to sort of, take advantage of all of them around the world in some use cases?
So there will definitely be synergies between GMT, using GMT to follow up observations taken by some of the specialty space missions like the Roman telescope, for instance, like I mentioned. But there's also definitely synergies between the 30-meter telescope, the European Extremely Large Telescope, and GMT. And so those can be used in concert. We're actually part of the US Extremely Large Telescope program, where GMT and TMT have partnered together and we're requesting some funding from the National Science Foundation. And what that will enable is that 25% of the time on either telescope can go to astronomers in the United States. And part of that is the hope that we can do some of these synergistic observations like you're suggesting. So if there's a supernova going off, and we'll maybe see it in the northern hemisphere for part of the time, and then in the southern hemisphere, to track it over like the course of a year, for instance, then we might that might be enabled by something like this US Extremely Large Telescope program. So the answer is yes, we definitely plan on doing that.
Thank you. Incredible what you guys are doing. Just incredible.
Thanks. Any other questions?
Other questions? Can everyone unmute?
Yeah, I raised my hand. I just wanted to know what is the maximum limiting magnitude of the GMT and the maximum redshift compared to the James Webb telescope?
That's an interesting question. So it depends on how long you're actually looking at the galaxy or whatever object that you're trying to view. Over the course of an hour, so in the B band, so that is about 440 nanometers, the limiting magnitude is about 30 magnitudes. In V band, it's about 29.79, so that's about 5,500 nanometers. Once you get into the infrared, like JWST, over an hour, it's about, I'm trying to remember the numbers off the top of my head. I think it's about like 20 or so. But if you observe for longer or continuously take exposures, like I did, for instance, in my thesis work, then it's definitely going to be able to go longer and probably reach what JWST is doing, if not go deeper. One of the advantages is that JWST has limited cryogenics in it, so its lifetime is limited, whereas with our infrared instruments, we can keep filling the cryogenics up, and we can also continuously upgrade the instruments, which we can't do for JWST since it's located at L2.
Outstanding. Thank you. Great presentation.
Thank you.
Breann, you had one of your images showed an adaptive optics camera setup camera, and then the next image on that slide showed what I will call, there you go, that's what I have on my telescope. I have the CCD camera with the filter wheel. Okay, so is that used for imaging, or is that purely a setup camera?
That's a great question. So this is this image that you're referring to up here. That is our commissioning camera. So we will use that to check our requirements. So I'm in systems engineering, so we have to make sure we hit all of our requirements before going on to the next thing. But we will definitely use this to image as well. So we'll use this to do some narrowband and broadband photometry. We'll also use this to take images of clusters and such. It will be a great way to get PR images, but it's also going to enable science. So it will be kind of a mixture of an engineering camera plus a science camera for those who want to use a visible light imager. Good question.
What filters is that going to have in it? And what level of a CCD camera is that? I mean, full frame or, medium format, or, you have a really big scope.
All great questions. So it is a full frame. So it will have about a 7 arc-minute field of view. It uses E2V detector, and it is sensitive from 0.35 to 1 micron. So it will have various filters like the BV, RI filters are the primary ones, plus others. And I think the pixel pitch is about 15 microns on the CCD they've chosen. I can't remember what the size of it is off the top of my head. I know it's I want to say it's 92.4 millimeters by 92.4 millimeters. So it's quite big.
Wow. Okay. Cool.
Does that answer your question?
Yeah, it actually kind of seems like that one aspect, it's like you got a normal camera, regardless, it's huge. It's comparative to what a lot of us use, right, sitting off of that scope, and that's pretty cool.
Yeah, for sure.
It looks like you were showing the secondary mirrors as the flexible mirrors in the adaptive optics system. Is there another flexible mirror in the path somewhere? Is that it?
That's a great question. So we will have multiple other mirrors in the path. So this is one of our AO instruments. And so right in front of it, we will have two additional wavefront sensors. One of them provides phasing information to keep all of our segments aligned and make sure that they are staying where they're supposed to be. And the other one provides at very, very fast rates, atmospheric aberration information to the telescope control system. So there are many layers to our wavefront control system. We have the one with the probes that I showed the example with first. We have our edge sensors that measure interferometrically with those lasers the relative offsets. The wavefront sensor is slow, the edge sensors are medium speed, and these two are very, very fast speed. So these take place at like 1 to 2 kilohertz rates, provide information. So very, very fast.
Breann, regarding the adaptive optics system again, is the use of a laser created guide star like outdated now? That wasn't, I didn't really see that discussed. And if so, why?
That's a good question. So I didn't include that here because it looks like a lot of the other lasers you might see from the observatory, but we will definitely have a laser launch system. So let me real quickly show you where those will be. So we'll have a constellation. It will consist of 6 lasers, and we'll have 2 coming out here, 2 coming out here, and then 2 more coming out here. And so, like I said, it will create a constellation of 6 lasers and 6 beams, and it will allow us to reconstruct what the atmosphere is doing over about a 20 arc-second field of view. And that's pretty large for adaptive optics. Good question.
Brianna, each segment of the mirror is what is the figure for each segment? Is it spherical? Is it a hyperbolic figure?
It's slightly parabolic.
Slightly parabolic. All right.
Yeah.
So in other words, it's like you have actually 7 independent mirrors that you're using together. Do I understand that correctly?
That's right. So if you put them all together, they all make the same parent parabola, but we basically take cookie cutters and cut out the sections of the parabola. So one of the interesting things is that, like I said, we'll have to take each of these segments off every so often to code it. But these 6 outer segments are all interchangeable. They all have the exact same optical prescription. The only one that's different is the on-axis segments, and we have a dummy mass to replace it.
All right, thank you.
When you guys are recoding one of those mirrors, will the telescope continue to be operable with just slightly less surface area?
Absolutely. So we'll see slightly less surface area, but overall, yes, we will definitely still be able to use the telescope. There is an idea of potentially creating an 8th segment and having that to replace whatever segment is currently being coded. But if we don't do that, we will take a small hit in sensitivity, but it won't be super drastic.
Will it only change sensitivity, or will it change field of view slightly?
It will also change field of view slightly, but most of the instruments, other than Manifest, don't really use the entire field of view of the 20 arc minutes. So it will impact it slightly, but it's not going to affect our science cases. Really, is more or less the point I'm trying to make.
How long will it take to recode the mirror?
That's a good question. We are estimating that from initially taking off the mirror, putting it in the coding chamber, coding it, doing our inspection and testing on it to make sure that it's a good coding, and putting it back, it will take anywhere from about 4 to 6 days.
Are you going to be building a recoding facility like you have in Arizona on site, or are you going to have to actually transport the mirror back to Phoenix to do that recoding? That's
a good question. We'll actually have a recoding system right here in this building. There's you can see this little area right here where we'll be able to take off one of the mirror segments. We'll have a large enough elevator to lower it down all the way, and then carry it or push it across in a cart to this building where we'll have a recoding station. And that will involve stripping the coating, It's magnetron based, so we'll then put the entire mirror cell on there and then coat it. And our baseline coating is bare aluminum, but we're looking into other options all the time as more developments are made.
What is the range of field of view, minimum to maximum, it can do the imaging?
It depends on the instrument, really. So for some of the adaptive optics instruments, so they're very small. So, you know, maybe as small as 5 arc seconds for like GMAG AOX, for instance. I think it's on the order of 5 for them. But it can go up to, for specifically for imaging, it can go up to about 6 to 7 arc minutes right now with ComCam.
Does that recoding? Oh, sorry. Go ahead.
The imager, a lot of our imager, a lot of our first light instruments are spectrographs. So a lot of the imagers really depend on what the science cases are for those specific instruments, and those are really denoted by and like determined by the instrument teams that are developing the instruments.
So it sounds like the adaptive optics is a tremendous growing field. How many telescopes are utilizing that technology today?
Many of them, and if they're not, there a lot of them, especially the big ones, they're upgrading. So I think every single telescope that's above 5 meters right now, and that might actually be a high upper limit. Every telescope above 5 meters, including the Palomar Observatory, is using adaptive optics. Not all the time, of course. Not all science cases need adaptive optics, but all of the large telescopes that I was talking about before use AO in some capacity.
Is there any scientific reason to use adaptive optics when you're shooting through the atmosphere?
Yeah, so if you're taking spectra, sometimes it's not always advantageous, especially if you have a slit. It's not always advantageous to have adaptive optics because sorry, what was that?
No, I'm sorry, go ahead.
Oh, sorry. So you, especially depending on what your slit size is, you might not necessarily want to have adaptive optics because that will bring your image size very, very sharp and very, very fine. And so you might not be able to fill your whole slit. And that's really what you want to do.
Breann, just real quick, on the seismic system that's going to be put into place, how many contact points are there for that? And are they concerned about getting hard spots in those? And if they do get a hard spot, how would they change that out? Because there's so much weight sitting on each one of those.
Good question. I think there's about 18, if I remember correctly. I'm not sure about the hard point thing that you bring up. Mm-hmm. So I know that we have that these are meant to be very essentially gliders for the entire system, but that's a really good point. And I don't know the answer off the top of my head, but I'm happy to get back to you with that answer.
Any idea how big an earthquake the telescope is designed to withstand?
Yes. So we're designed to withstand. So we have 3 different levels of earthquakes. We have our normal earthquakes, which, you know, those happen 6 times a month. So those aren't really a big deal. And all the way up to our survival level earthquakes, where things will break and we just want the telescope to survive. And I think that's on the order of a magnitude 7 or 8, possibly higher than that. But we have thoroughly thought about all of this. We have a list of things that absolutely cannot break if we reach one of those survival level earthquakes, like our primary mirrors, for instance. Like I said, it takes about 4 years to make one of those. We can't break them. So we are taking all of these seismic levels into account, and all of our instruments and and all of our other subsystems are looking and making sure that they're able to withstand those very powerful earthquakes if needed.
Breann, as the deputy systems engineer, what stresses you out? What keeps you up at night and being able to deliver this to all of the investors politically in this whole mess?
So I think that, you know, one of the most complicated but very unique parts of our telescope is the fact that we have these seven secondaries and 7 primaries. And so one of the really hard things, especially given the masses and given everything that's going on in the telescope throughout the night, is making sure that when we're taking adaptive optics observations, all of our segments remain phased with each other. That is the primary and the secondary. We have, like I said, we have a lot of wavefront sensors talking to each other and a lot of the information going into the control system. So it's just, I think that's probably the thing that is, I wouldn't say it worries me, but it's definitely the most complicated thing and definitely one of the scariest things to address, in the sense that there's just so much going on with it.
And probably the largest, a very large potential for human error, human input.
I think that's true for most projects, right?
Breann, a question from the chat. What is the primary focal length, secondary, and is there a Cassegrain?
There is no Cassegrain. So this is a Gregorian design. It's an aplanatic Gregorian. So underneath our mount, we actually have a Gregorian instrument rotator, and that's where all of our instruments lie. So underneath all of this right here, the focal length, it's about 200, the total focal length is about 207 millimeters, or 207 meters, sorry. About 207,558 millimeters total, I think, or something like in that range. So it's quite a long focal length. The interesting thing is that, so the total F number, if that is helpful, is about 8.16. We have a very fast primary. This is about f.7. And our secondary helps slow things down a little bit to get it to the final f 8.16.
Is there a polar axis? It looks very altitude azimuth.
It is LAAS.
Okay.
Regarding the laser guide stars, do you have to introduce sodium ion in the atmosphere for that to work, and how high, and how do you put it up there?
No, there's enough sodium in the atmosphere, and our requirement is actually to have a very, very small amount of sodium in the atmosphere, and we're still able to meet our requirements based on what we've been able to do in simulation. So we're not concerned about it. We don't have to add additional sodium into the atmosphere. What we have up there is good enough, even during the low points, and that tends to go with some of the solar cycle. So I think we're set.
With some of the, we're talking about political, a pretty wide field of political issues at some level, working with all of these different countries all over the world. Is there any concern that we end up with a problem like we have with ISS, where we suddenly have a falling out with somebody, becomes a problem? Is that a realistic future?
I don't think so. We've had cordial relations between all of our partners. A lot of them work together, actually. So CASI in Korea works very closely with UT Austin. They've been working on instruments together for quite a long time. And they have some instruments like the Igrans instrument on Gemini that they've developed together. And we've always had very cordial relationships with all of our partners. We make sure we try and include all of our partners in our big decisions. And when we have events like our annual community science meeting, for instance, we make sure that we include partners on the organizing committees and have speakers from our partners and so on. So I don't think, we're not really worried about it. We try our best to make sure that all of our partners work together. So I don't think this is a big concern. Everyone is very cooperative with each other.
Cool. Yay.
Yes, for sure.
Another big player in adaptive optics is the Department of Defense. Do you come up with restrictions like the ITAR on exchange of information with some of the countries? And do you share information with the Department of Defense on the technologies?
So All of our information on our adaptive optics system and such is open source. So there was actually a conference about 3 weeks ago that a bunch of us went to, and we in public presented all of our work. So we're not trying to hide anything. We do definitely adhere to ITAR standards and everything. So we make sure all of that is good. But we also do collaborate with other members of the community, as for instance, the European Extremely Large Telescope or the 30-meter telescope come up with ideas. We talk to each other. We do some of our prototyping of our adaptive optics systems on the Magellan and the Keck telescopes, for instance. So we really do try and act as an adaptive optics community.
Thank you.
Given the advancement of the adaptive optics, do you think it's still economically feasible to put a second generation Hubble around the Earth, or that's no longer in the cards now?
So I think that having space-based telescopes can be very, very powerful because they allow us to do things that some ground-based observatories can't. You don't have to worry about the atmosphere in space, and you can also get to much, much, much colder temperatures in space, like at L2, like JWST, than you can around the Earth. The other great thing about Hubble and such is that you can observe pretty often, whereas we're limited to day and night cycles, right? For our observatories, so we can only observe certain hours during the day. Whereas you can be a bit more efficient with some of the space-based observatories. JWST, for instance, can observe all the time.
How much are you affected by weather?
Excellent question. So our site is very high and very dry. We have over 300 clear nights a year, so we're not really that strongly affected. The biggest things that we get are sometimes we get winter storms. We just had one actually a few weeks ago where we got meters, literally meters of snow on the ground. And it did knock out some of our power up there on the site right now. But this happened with every observatory down in that area. But we're not really too strongly affected. We are still able to get excellent science. It's a wonderful site. The temperatures insanely stable. When I first looked at the data, because I'm the keeper of all the weather data, I was surprised because the nighttime temperatures were so stable. I thought I did something wrong to the data, actually.
What's the altitude at the site?
2,514 meters.
How do you
about
prevent
8,000
snow?
feet.
Very specific.
How do you prevent snow from falling in on the telescope when you open the dome?
Excellent question. So to answer this specific one, it's I was just typing about this like 20 minutes before I gave this presentation. That's the only reason why I knew that specific answer. But for the snow, it's kind of hard to see on these drawings, but we have a slant to everything so that it's always slanting away from this slit of where the telescope opens up. More importantly, if there's ever snow on top of this, we will go and we can send drones up, for instance, to check to see if there's a lot of snow anywhere near the slit. And if needed, we can we might not open, or we can send people up on the top of this to actually go and sweep it up if needed. We do take a lot of safety into consideration in here. So we're never going to do anything if it's dangerous to either humans or the telescope.
Would it be worthwhile considering an engineering solution of de-icing on the actual roof so that that could be solved without having to do anything?
It's a possibility. I don't know if that's in the cards right now, but it's certainly a possibility. It also wouldn't be that expensive. We also have a heating system that and an HVAC system that runs throughout the entire enclosure. So it wouldn't be that challenging to put something just right up here to try and heat the walls or heat the roof a little bit if needed. So yeah, there's definitely engineering solutions that we could put.
I just wondered if it was being considered instead of you know, oops, we send up a drone, oh crap, there's snow on the roof.
No, I mean, even if we have a heating system, even if we have a de-icing system, we will still send a drone up just to be safe, just because safety is our biggest concern at the observatory, to make sure that nothing ever harms the telescope or humans. But yeah, we will come up with an engineering solution. I just don't know if one's already been proposed.
Breann,
Mhm.
This is Dave. Thank you first of all, thank you so much for doing this. Everybody's really excited about your presentation this evening. I can tell you from the chat. Also, I know that JST's main thrust was to look at the Big Bang. What is your main thrust for science for this telescope? What do you think?
So again, that depends on instruments. So we will definitely have, so one of our instruments actually has it's called the cosmological spectrograph. It's GMAX. So definitely studying cosmology is one of the main drivers of this, looking at supermassive black holes and so on and so forth. But we also have a lot of instrumentation that will go, and one of the hot spots of astrophysics right now is, of course, extrasolar planets. So looking at the expanding the masses that we're going to see from radial velocity measurements, figuring out what the atmospheres of planets are, and so on. So this is also a great synergy with JWST, because this is also one of the main science drivers of that telescope. So like I said, it depends on the instrument. There's no one like all-encompassing science big driver for us, but it depends on the science teams. But we cover a large spectrum of them.
Breann,
I would
unit
love to see your face
showed.
finished.
The unit you just showed, with, you know, it's huge. It's like what, 20 feet tall. That's the actual imaging device. How does the telescope send data to that? That thing's monstrous.
It is a monster. So what this does, this sits on something called a Gregorian instrument rotator. So this instrument is going to essentially sit under our mount. So here we go. It sits in, you see this red color thing right there?
Yeah.
That's where our instruments, one of our instruments will sit. When we deploy it, we will move that entire mass that you saw here into focus, and the light will go from the primary mirrors to the secondary mirror, down that hole,
and down the hole
to the top plate of this instrument. So there's and then from there it will be this particular instrument has two different arms, a red arm, a blue arm right here, and a red arm right here. And so it will divide the light, and the data will be collected at the detector. So some of these are massive instruments. It's quite insane.
Wow.
Yeah.
Are they all able to expose simultaneously? It's all split, or are they moved into?
So they have to be moved in. Some of them, not all of them do. So some of them sit on the very top of our instrument rotator, and they're like on there, and they just rotate with the rotator. But we have a tertiary mirror that comes down and directs the light. And so we don't divide the light between the instruments. We just have one instrument taking data at a time.
Okay.
Wow.
So what is the final cost of this system when it's all said and done?
That is a number that I don't know, and I'm not, I really don't know what the number is off the top of my head. It is
going to be cheaper than JWST, or
That's
more expensive?
Not more expensive. Much more. It's got to be.
Well, what was the final cost of James Webb?
I think it says 10 billion something.
It will be less than 10 billion. For this telescope, it will be less than 10 billion.
You're going to lowest bid contract?
The lowest big contract? Well, we have some huge contracts, right? Building our entire mount, building our entire enclosure. Those are two of our largest contracts. And then we have each of our instrument teams are contracts as well. So But again, we're very collaborative with all of our contractors, and our primary mirrors too is another one of our biggest contracts.
I don't see Ingersoll Rand being a lowest bidder.
Breann, thanks. We're going to have to take care of a little business. You should sign up for the prizes if you want to stay for a few minutes. But thank you very much. It was awesome. You answered everyone's questions. Yeah. It was really, really nice. Thank you so much.
Yeah, thank you all.
Great presentation.
So cool.
Wonderful.
Okay. Well, let's see. Wait a minute. Was there another question here? A lot of thank yous in the chat. Fantastic stuff in the chat, which I think you have access to. So if you want to look, there's a couple of maybe questions that I missed. I don't know.
Awesome. Thanks.
Okay. Has everyone signed up for the drawing? Or do you need me to put the? See if I still have it here. Yeah, just drop the sign up for the drawing in the chat.
Somebody sign up, Breann.
Okay, so
he needs a laser.
Everybody's in. Okay, let's see. Okay, so we'll close that out. Why don't you everyone chat for a minute while I go and get the data from the data place, wherever that is.
We should make all of our speakers automatic prize winners.
I was going to say, that's what I said. We need to sign her up, right? Or like sign her up 4 times automatically so that she's got 4 times as much chance.
Because she needs a red light, you know.
She needs a laser really badly.
Yeah, she needs to get a laser, right?
Just get a swag bag, you know. Just give her a swag bag.
We'll give her a shirt.
Probably shoot down planes with the lasers they're using.
She doesn't want a green laser. They have those special amber militarized lasers.
So, Breann, how does it feel to be a job where the realization of the project is still 8 years away?
Sometimes it's a little overwhelming because we have a lot of work to do within the next 8 years, but it's also exciting because it's such a big project, and being able to be involved when we're still in like the design phase for some of the subsystems is really exciting because like I get to make my mark on the telescope and continue to make my mark on it, if that makes sense.
Oh, so yeah.
I hope you sign your name on it.
Right on the primary mirror segments. No, I'm just kidding.
There you go.
Put it on the back. Put it on the back of the mirror. Nobody cares what's going on. No.
In the middle of 2030, somebody's going to be troubleshooting some image. They're going to be trying to figure out what's going on, and all of a sudden they're going to find this signature on the corner of one of the mirrors from done within the freaking laser etcher. Like, Breann was here.
Yeah.
Yeah,
I would do it. I would do it.
Engineers in automotive industry used to, when they're doing their molds for headlights, they put their name in the headlight. So when they
in the headlight.
Yep.
That's pretty awesome.
Yeah, that's been going on forever.
Yeah.
That's why I made the joke. It's like, you know, at some point in time, most engineers sign their work. You just don't necessarily get to see it. It might be an Easter egg. It might be hidden, whatever. But most of us have a tendency to hide our name somewhere in there someplace.
Hey, Tim,
Okay, so
Tim, what is your...
I've grabbed everybody's name and I've dropped it into our spreadsheet. And the first winner is Mary Snooty.
Yay.
Woo.
Mary, what you get?
Mary here?
Yeah, I'm here.
Hey, how are you?
Good to see everyone.
Okay, so
do we have an Alicia tonight?
Yeah, Alicia's here. What did she win, Alicia?
She won an Amazon gift card.
Amazon gift card. Okay, so let me find her and
so she can buy an Amazon.
Numbers, line 7.
Thank you. Okay, Krista Dobrovic.
I am here.
Yay.
You are here. Okay.
Yeah.
And what did Krista win?
She won a LAAS hat.
All right.
Hey,
Hey. Fall
you got a
cap.
hat coming. Dan Schwartz is our next winner.
He won a laser.
Oh, the good one.
Dan here?
Yeah. Go Dan.
You
Okay, I see him. I see him. Let me find him here.
You there, Dan?
Zero. Who's zero?
You double clicked at some point.
Oh, I think you have
there's another one.
delete the row.
There we go. Edward Graff.
Wow.
Well,
that's fantastic.
New member right away. That's cool.
That's great.
Yeah.
I'll have to join the club more often.
What did he win, Alicia?
A Celestron Observer's map of the moon.
Fantastic. That's
All
great.
right, that's cool.
You'll never get lost on the moon again.
How many more do we have, Alicia?
2 more.
2 more. Okay, let me find Edward.
Line 3.
Thank you. Shane. Shane's here. I saw him somewhere.
2.
Did he go away?
I don't
We
know.
have a Shane.
Oh, no, there he
we have
is.
a Shane.
I see him.
there.
Shane Winter.
He's there.
Oh, I see him. He's muted. Hey, he's awake.
Hey, you winner. What's he got?
Somehow.
A red flashlight.
Red flashlight coming to you. All right.
Sweet.
So
Very nice.
one more.
Mm-hmm.
Dave Yackerson.
Oh, I won something. Wow.
All right.
He won a gift from the LAAS store.
Okay, something from the
Thank
store.
you.
All right. Well, thank you everyone for coming. We will leave the chat is open for however long Zolly wants to leave it open. If there's more questions that Breann wants to answer, she can. If you have to go, we certainly understand that as well. So with that, I think we could actually end the meeting and just turn it over to everyone to just chat. So Zolly, you want to end the recording?